Okay, so welcome to this next video in the playlist on synaptic mechanisms. In this video, what we're going to do is now turn our attention away from synaptotagmin binding to syntaxin 1, and we're going to talk about it binding to phosphatidylserine in the membrane of phospholipids. Okay, so if we draw our vesicle here that is docked at the membrane, so here's the plasma membrane, and it will be docked by core snare complexes. Then if we draw our synaptotagmin in here, so here are the two C2 domains, the C2A domain and the C2B domain. Right, so when calcium goes up in the cytoplasm, we have already seen that calcium is going to bind to the C2A and the C2B domains of synaptotagmin. So free calciums are going to bind to C2A, okay, so free calciums are going to bind to C2A, and 2 calciums are going to bind to C2B, okay, right. Now, we've seen that what this triggers is synaptotagmin to now bind to syntaxin 1. What we're now going to see is that it also triggers the C2A domain to start binding to phosphatidylserine, which is in the phospholipid bilayer. Okay, so I will discuss with you what the structure of phosphatidylserine is. Okay, right, so we'll go down here then. Right, so the phospholipid bilayer is made up of phospholipids. So let me tell you what a phospholipid is. Well, let me remind you what a phospholipid is. Phospholipids are often drawn in cartoons like this. Okay, so they have 2 long chain carboxylic acid tails, and they have a glycerol backbone, and then a phosphate group bound to the 3rd hydroxyl group of the glycerol molecule. Okay, so in red here is the phosphate group bound to the 3rd hydroxyl group of the glycerol molecule in green here, okay? And then off the 1st and 2nd hydroxyl groups here, you have long chain carboxylic acids bound, esterified. Okay, now the phospholipid bilayer basically consists of loads of these phospholipids all stacked together in a row like so. So you have loads of phospholipids. Now that would be a single layer of phospholipids. What you do is you actually create another layer, which is why it's called a phospholipid bilayer. So you have these 2 layers of phospholipids where their orientations are 180 degrees opposite, basically, and the layer underneath has its hydrophobic tails sticking in the opposite direction. So both of these phospholipid layers, let's say this is the outer leaflet, okay? So this outer layer of phospholipids is known as the outer leaflet, and this is the one which faces out to the extracellular fluid. So let's say this is the extracellular fluid above here, and this is the inner leaflet of the phospholipid bilayer. Okay, so this is the inner leaflet which faces towards the cytoplasm here. Okay, right. So what we can see is that these hydrophobic tails here in orange, they all face in towards each other to make what's known as the hydrophobic core of the phospholipid bilayer, okay? So these hydrophobic long-chain carboxylic acids, which are esterified to the glycerol molecules, do not like interacting with water. It's not energetically favorable for them to interact with water molecules. Water is far more energetically favorable to for water molecules to remain bound with hydrogen bonds to each other than to interact with these long-chain carboxylic acids. So instead, the long-chain carboxylic acids all end up interacting with each other, which is energetically favorable, and the polar heads of the phospholipids. So these phosphate heads that are bound off the 3rd hydroxyl of the glycerol molecule, those point out towards the extracellular fluid and the cytoplasm, and those will interact with then the water molecules in an energetically favorable manner because they have a negative charge, basically. So these have negative charge. Now, what I now want to do is draw the actual structure of one of these phospholipids out for you and show you how we modify it to make phosphatidylserine. And by the way, the old name for a phospholipid molecule, which is what one of these is, so this is a single phospholipid here. The old name for a phospholipid molecule is that it's a phosphatidate molecule. So that hopefully gives you some intuition as to what phosphatidylserine is. Phosphatidate. Okay, so phosphatidate is going to be a modified, phosphatidylserine is going to be a modified phosphatidate molecule. Okay, so let's get a new piece of paper and discuss what the actual structure of a phosphatidate molecule is, atom by atom. Okay, so the molecular structure then. So you start off with glycerol. And glycerol is a free carbon molecule which has hydroxyl groups coming off all 3 carbons. One hydroxyl group coming off each of the carbons. Now I haven't drawn them as hydroxyl groups. Of course they would have to have a hydrogen coming off for that because they're going to be involved in bonds to other structures. So these first 2 hydroxyl groups here are involved in esterification reactions in ester links to long-chain carboxylic acids. This is meant to represent a long-chain carboxylic acid. So in turquoise here, this is a carboxylic acid which has been esterified to this first hydroxyl group of the glycerol molecule, and this R group here is supposed to be a long group basically. So this is a long chain carboxylic acid. Okay, and off this first carbon of the glycerol molecule you will also have hydrogens coming off it. Again, off the second carbon you have a hydrogen. Now, coming off this hydroxyl group of the second carbon, you then have another long chain carboxylic acid coming off here. So I'll put R prime there to denote that the R group may well be different from this R group up here. So again, this is another long chain carboxylic acid. And the biochemist's name for a long chain carboxylic acid is a fatty acid. So you might also hear long chain carboxylic acids referred to as fatty acids. Okay, now finally, in a normal phosphatidate molecule, off this third hydroxyl group you have, linked by a phosphoester or a phosphate ester bond, you have a phosphate group coming off here, and then hydrogens off there. So this bond here is a phosphoester or a phosphate ester more properly, but it's often abbreviated to a phosphoester bond. Okay, so, and this is a phosphate group that we've got stuck off here. So this is our phosphate group. Okay, now that is the structure of a phospholipid or a phosphatidate molecule. So this is phosphatidate, okay, or a phospholipid. Right, the reason I've drawn, you might ask, the reason why I've drawn these 2 carboxylic acids, or long-chain carboxylic acids, going off in opposite directions is because that's more true to reality. You will have one going off this way and one going off this way. They won't go off in the same direction simply because it will lead to overcrowding. Okay, it's more favourable for them to go off in opposite directions. Now, how do we modify this molecule to create phosphatidylserine? So we're trying to find out what phosphatidylserine is. Well, basically what we do is we bind a serine amino acid to this phosphate group here, and specifically to this free hydroxyl group of the phosphate group here. So let me remind you of the structure of the amino acid serine. So here's the amino group. Okay, here's the alpha carbon with the carboxylic acid group down here. So that's just the core generic structure of an amino acid. Here's the hydrogen coming off the alpha carbon, and then the R group of serine is that you have a methylene group like so, and then a hydroxyl group coming off here. Okay, now what you are going to do is you're going to make a phosphoester bond between this hydroxyl group of the serine, so this is serine here, and the hydroxyl group of the phosphate group over there. So we're going to take off the hydroxyl group from this phosphate group, okay, You're also going to take off the hydrogen from this hydroxyl group here, and you're going to combine them together to make water. So this is going to give water, H2O. Then what you're going to do is you're going to link this remaining oxygen here. So I'll get this purple line here. You're going to link this remaining oxygen to this phosphorus atom at the center of this phosphate group. And that's going to be then how you link serine onto our phosphatidate molecule to create us phosphatidylserine. Now, I hope what I've shown you, therefore, is that this is effectively just a modified phosphatidate molecule. In fact, if we go back to our original cartoon, here are the two long-chain carboxylic acids. Okay, so these are the two long-chain carboxylic acids here. Okay, and then we have our glycerol molecule here. Then we have our phosphate head here. Okay, so this is this bit. And now what we have done is we put on this serine group here. So how should I draw serine? I'll just draw it as a triangle, maybe, just since it's a cartoon. So this blue triangle, as I'm going to draw it, is the modified group that we stuck on the end of this phosphate group. And this is phosphatidylserine, often just abbreviated to P for phosphatidyl and then S for serine. So phosphatidyl is abbreviated to P, and the serine is then the S here. Okay, and that's a usual constituent of the phospholipid bilayer. So, what happens then? When calcium goes up in the vicinity of the synaptotagmin protein, calcium is going to bind to these two C2 domains of the synaptotagmin protein, C2A and C2B. 3 calciums will bind to C2A, 2 calciums will bind to C2B. C2A will then start binding to phosphatidylserine molecules in the plasma membrane. So, if we draw the phospholipid bilayer here, what you'll have in the plasma membrane is phosphatidylserine residues here. So here's the phospholipid, and then here's this blue carbon here. And what will happen is, if this is our synaptic vesicle here, then if this is our C2A region, it will bind to that phosphatidylserine. So let me label everything up. Okay, so in blue here, we have our serine stuck on the end of this molecule. Red, we have our phosphate group. Green, we have our glycerol. Okay, and orange, we then have our phospholipid, our hydrophobic tails of the phospholipid. And in purple here, we have our synaptotagmin. Okay, these two C2 domains denoted as these two balls. So this is C2A here, and this is C2B over here. So this is one of the mechanisms by which C2A is going to lead to the fusion of these two these two membranes together, the vesicle membrane and then the plasma membrane. And I realise this diagram is slightly confusing because here this represents a single membrane, and here I've drawn a single line to represent the phospholipid bilayer of the vesicle. Don't let that confuse you. This one has been bumped out so that I can show the phosphatidylserine molecules in it. Okay, so we'll continue this discussion in the next video, where we'll look at some experimental evidence that phosphatidylserine combined to this C2A, C2 domain of the synaptotagmin protein.